Okay, on to the second and final video for the photons topic. And we're going to look at the application for this topic, which is X-rays. So let's talk about how X-rays are produced in an X-ray tube. And we'll start the journey here at this little filament here, which is called the cathode, which is a filament that acts as a source of electrons. So this filament is attached to a low voltage power supply, and it acts just like a light bulb would in the lab. Apply a voltage to the filament gets hot. As that hot filament is basically, electrons can basically bounce to very near the surface, and that basically gives a source where electrons can be very easily pulled out of the atom. Now this filament, just like in a light bulb, is all contained within a glass tube vacuum, and that's basically so that any electrons that get produced here don't lose energy in collisions with air molecules. And the chemist might also realise that if this was air in here, that could react and cause the hot filament to catch fire and burn, which would basically blow the filament. So we need to have this all enclosed in a vacuum so that the air can't either cause the filament to burn or electrons to lose energy in collisions with air particles or air molecules. So, opposite, if you like, this cathode filament, we have our target, or also known as our anode. And what we do is we apply a higher voltage, so normally several thousand volts, between the cathode filament and this target. This would be the positive end, the target. The negative end is the filament, causes the electrons to be repelled from the negative, accelerated towards the positive at very high speed. So the electrons slam into this target here, which is this dark bit here indicated by B. Now, this target needs to be very hard because it needs to withstand the constant bombard of electrons, and it also needs to have a very high melting point because we get a lot of heat produced in this process, and if it didn't have a high melting point, it would melt. So we use tungsten for that target because of its high melting point and hardness. The tungsten is contained within a solid piece of copper. Copper is used here because it is a great conductor of heat and electricity, so it's good for conducting the electricity from the high voltage power supply, but it also conducts the heat away very well from the target. And on the outside of the glass tube, we usually have cooling fins to increase the area so the heat can be dissipated more quickly from this target. Because basically, as I say down here, when the electrons strike the target, most of their energy is converted to heat. So 99% of the energy goes to heat. A small amount goes released in the form of high energy photons, which we know as X-rays. So I think that covers all the key parts of an X-ray tube and basically how they're used to produce X-rays. Just in terms of, if you like, the theory of how the X-rays get produced from the collisions in this target, what essentially happens is we'll use this diagram up here at the top. We have an electrons and they get fired at very high speed into the target atom, and they will pass often very close to the nucleus, maybe not that close. Sorry, I'll just draw that again. They will pass very close to the nucleus and basically be deflected or lose energy in those interactions with the nucleus. We know energy must be conserved, so if the electron loses energy, it must go somewhere, and that energy can be released in the form of a high energy X-ray photon. So just as when we talked about electromagnetic radiation, we talked about light and electromagnetic signals are generated through the acceleration of charges. In the same sense here, as this electron passes near the nucleus, it decelerates. That energy is converted into an X-ray photon because it has a huge amount of energy. We can get a photon released with also a huge amount of energy. We'll talk exactly about how much energy in the next slide. So let's look at what the X-ray spectrum would look like. So sketch a graph of the spectrum from an X-ray tube showing the three main features of the spectrum. So if we looked at the frequency of the X-rays that are released versus the intensity, which is basically a measure of the number of X-ray photons, we would see something that looks like this curve here in blue with these little features here. So what exactly are those features? Firstly, we would see a continuous range of frequencies, which has some fancy German name called the Bremsstrahlung. My German isn't very good. Yours might be better. So we would see a continuous range of frequencies. We would also see a continuous range of frequencies up to the second point, a maximum frequency F max. So we would see that there would be a frequency maximum which they would go up to. Now that maximum frequency is determined from what we've got over here. We know the energy of a photon is given by HF. And the energy of an electron is the work done equals, the maximum energy of a charge is work done equals the charge times the voltage, so work done equals Q delta V. So if we're talking about the energy here of an electron, we're talking about E, the charge on an electron, times by the voltage. So the maximum amount of energy that the X-ray photon can get is if all of the energy of the electron that was being fired at that target is lost and converted to the photon. So HF max, the maximum frequency, which is the maximum energy, would be equal to E times, or little e, the charge on an electron, times by delta V. So rearranging that, F max equals E times delta V on H, which is this relationship up here that you need to be able to show. So that you won't see a photon with more energy than that because the photon can't end up with more energy than the electron that was being fired at the target had. And finally, the third feature that you will see on the spectrum is these peaks at certain, so these high intensity peaks at certain frequencies. You just need to know they exist. You don't need to know the cause of those. It's basically related to preferential sort of energy arrangements within the atom, which means that they are more likely to occur, but as I said, you don't need to know that. So that really covers the main things we need to know about the X-ray spectrum. Obviously, the intensity of X-rays is decreased, or attenuated is the fancy word for decreased, as they pass through matter by scattering and absorption. So the way that we can see with an X-ray is the X-rays, as they go through our bodies, get basically scattered or absorbed by things particularly like bones. So they can't travel through those, but they can travel through the fleshy parts, and that lets us build up an image of our skeleton and our internal parts. We're going to cover that more in the next slide. Okay, time for a crash course in being a radiographer, or how to use an X-ray machine. So we're going to quickly cover the things that affect the attenuation or the absorption of X-rays in our tissue. We're going to talk about how we can increase the penetrating power, which we call the hardness of X-rays, so that they can basically penetrate further through our tissue. We're also going to talk about how we can increase the intensity of an X-ray so that we can get a really good X-ray picture really, really quickly. And we'll talk about some of the reasons why we might want to get a nice, clear and quick X-ray picture. So firstly, 3 factors affect the attenuation or the absorption of X-rays in the body. The density of the tissue. So the greater the density, the greater the attenuation. So something like a tumour might be denser and therefore absorb X-rays or attenuate X-rays more than the normal tissue surrounding it, so that it will show up in an X-ray. The thickness of the tissue will affect the attenuation. So you'll need more X-rays or more powerful X-rays if you are going to image your leg, maybe as opposed to your hand, because your leg is obviously much thicker. And finally, and probably the most interesting, is the atomic number of the elements making up the tissue. So the greater the atomic number, the greater the attenuation. So one of the reasons bones show up is they contain a lot of calcium, which is about element number 20, I think, yeah. Whereas most of our body is made of carbon, oxygen, hydrogen, which are all sort of 6, 8, 1. So the heavier elements show up more clearly in the X-ray. Things like metal screws and all that other bits and pieces that are in our body will also show up really well in an X-ray because of their higher atomic mass. One way they use this is something called a barium mule. And this little picture here shows a barium mule. If you've got a problem with your digestive system, they'll give you this mule which contains barium. Barium, I can't remember the atomic number off the top of my head, but I think it's about, well, it's a fairly high one. I think it's about 70, but I could be wrong there. And it shows up really well in X-rays. So if you eat this barium meal, it'll get distributed all through your digestive system. If there's a problem in your digestive system, so say you've got an ulcer and there's a leak if you like, or you've got a perforation in your bowel or something like that, that barium will sort of basically leak out from where it should be. That'll show up really clearly in an X-ray, and you'll be able to diagnose that possible problem. So here you can see the sort of workings of the digestive system showing up really clearly in the X-ray because of the presence of barium in them, because the person was given a barium meal to eat before this X-ray was taken. Okay, so if we want to increase our penetrating power, as I said, we call that our hardness of our X-rays, we need to give them more energy. To give the X-rays more energy, we need to give the electrons that are basically being fired at the target more energy, because the more energy the electron has, the more it can lose, the more that can get converted into an X-ray. We talked about that in the last slide. So if we increase that high voltage power supply, the delta V, we'll increase that energy, which will increase the frequency of the X-ray. So the greater the frequency, greater energy, the further it can penetrate through our flesh. Finally, if we want to increase the intensity of the X-rays, and we often want to do that so that we can get a really good picture more quickly, so we need less exposure time for that X-ray, because if we can lower that exposure time, that means there's less chance of a patient, say, for example, moving during the X-ray and then blurring occurring. Well, we can achieve that increase in intensity by increasing the filament current. So if we increase that filament current, that filament gets hotter, more electrons get excited near its surface, so more electrons can be, if you like, sucked off that filament towards the target. That will increase what we call our tube current, so that's the flow of electrons between that filament and that target. Therefore, more photons, more X-ray photons get produced, so we have a greater intensity of our X-rays, so that we can get a better picture quicker, to say that in simple terms. So, if you want to be a radiographer, you're probably going to have to go to university and study that, but that's a very quick introduction to being a radiographer. Cheers.